Okay, for this last video, we look at kinetics of photochemical processes. So, essentially, how does light factor in as a react? So we can break our photochemical things into two processes, a photophysical process and a photochemical, just like we did with heterogeneous catalysts. We talked about physisorption and chemisorption. So we'll spend the majority of the time on photophysical, where light absorbs. This leads to electron excitement, whose energy then can be released through a variety of relaxation mechanisms to get down to original state. But first, we need to set the stage with some equations. So energy of one photon of light is essentially h nu, where nu is equal to c over lambda. So energy of a photon is hc over lambda, and units of joules per photon. For energy, h is Planck's constant, which is joule seconds. C is the speed of light in meters per second. Nu is the frequency of light, and usually inverse seconds or hertz. And lambda is the wavelength of light in all sorts of units of distance, like meters or nanometers or whatever. To scale up the energy of a photon to a mole, we're going to say energy of the photon times Avogadro's number. It's going to be a joule per mole photon, and it's going to be call that Einstein. So, and then another common unit is intensity, which is energy per unit area per second. So as you're looking at energy delivered to a square unit per second. And because joules per second is a watt, intensity is often given as watts per centimeter squared. So how much watts of energy can be delivered to this centimeter square, this little square, this patch of surface. Now thinking of the simplest photochemical process, where A, we shine light, it goes to products. Our rate, of course, would be the change in A with time. And we're going to look at the initial absorption times 1,000 divided by L. So the intensity of the absorption times that. Intensity of light absorbed in Einstein per centimeters cubed, centimeters squared seconds. L is a path length in centimeters, and 1,000 is what we use to convert from centimeters cubed to liters. So we get essentially a term of molarity per second. That same reaction rate that we would use anyways. So intensity is, our watts, essentially joules to joules of photons. So using our Beer-Lambert law, says that the intensity of our transition, our transmittance is our initial intensity times 10 to the epsilon path length concentration. Essentially, the intensity of light transmitted is proportional to the original intensity times 10 to the inverse power of the molar absorptivity times the path length times the concentration. Now, because the intensity absorbed is your initial intensity minus the intensity transmitted, we can say that intensity absorbed is initial intensity times 1 minus 10 negative epsilon LA. This is still a pretty complex equation. Now, we can use a series of expansions to simplify this. A series expansion says e to the x equals 1 plus x to the first over 1 factorial, x squared over 2 factorial plus on x to infinity over infinity factorial. Convert this to a log as 10 to the x. 1 times 2.303 x to the first over 1 factorial, 2.303 x squared over 2 to the prime factorial, and so on. So 10 to the negative ELA equals 1 minus 2.303 ELA over 1 plus 2.303 ELA squared over 2. And if we keep going if we keep A small enough, it will simplify to essentially this. So if we make sure that A is not going to overwhelm the detector, if A is a small enough concentration, A squared times epsilon times path length times 2.303 is a rounding error. But this, we can't just ignore that. So we can make this assumption that place that. So initial absorption is EI, it was I0 times 2.303 epsilon L A. Plugging that in, the path length goes away. And integrating for A, we essentially have A equals, concentration A is equal to A naught, E to the negative 2.303 I0 E times time, which essentially comes down to I naught is not going to change, epsilon's not going to change, 2.303 is not going to change. So all that's just our K effective. So A, concentration of A is equal to initial concentration, E to the negative KT. That really starting to look like something we've seen before. Now, we have some Jablonski diagrams. Named after Alexander Jablonski, this schematic shows the various excitation vibration states within a compound. It's composed of our group's state singlet 0, and for our purpose of the first excited state singlet 1, and the excited triplet state triplet 1. Now, singlet states come from unpaired electrons with opposing spins. Triplet states comes from unpaired electrons with matched spins, often come from a spin flip or spin inversion. So essentially, look, ground state, we can vibrate from any of these ground states, and we can be excited to the first excited state, and just electron just moving up, and then that's keeping the same spin. We could keep moving up, but we're not going to look at the second. And it can relax back down to any of these states. But it could also have this inversion where it spins up and then it inverts. So the down electron has gone up. So now you have 2 up electrons, and now it takes a little bit longer to relax back down. So we have a whole bunch of different relaxation mechanisms. That the green is excitation, the red is fluorescence back down, yellow is vibrational relaxation, non-radiative relaxation can quench the back down. But you have this intersystem crossing, where it's like it doesn't want to go there, and that's it. Might take a little bit longer. And so we have some phosphorescence right there to go from our excited triplet back down. Okay. Now, after an initial absorption process, a variety of relaxation, we can have simple radiative transition, singlet to singlet, release the light, fluorescent to get back to ground state. Possible to have intersystem crossing, I just mentioned, where the electron spins. There, it has to phosphoresce back down. And because the spin flip is required, it's almost 1,000 times slower. The internal conversion or non-radiative decay is another possibility, where the electron undergoes vibrational relaxation. Finally, collision quenching can occur, releasing energy through the essentially molecules bumping into each other. All these processes are competitive and can be described through the rate law. by looking at the studying the quenching rate as a function of Q, we can learn about our KF, our fluorescence. So we have quenching at KQ, we have intersystem crossing, we have phosphorescence from KP and T1, we have the intersystem crossing from T1 back to S. The one we really care about is usually the fluorescence. So all the things S1 can do is it can absorb to form S1 from S0, it can fluoresce back down, intersystem cross, it can intersystem cross. Let's say what's that? We can IC back down. So internal conversion, such a non-radiative decay. So we can intersystem cross, and then of course can quench by hitting another molecule Q. If constant illumination is used, we can say that S1 will remain essentially constant, and thus we can use the steady state approximation. Essentially, the S1 is going to be constantly formed, so even though it's undergoing all these decay states, it's going to be essentially held constant. The change, it's not going to change because every time it's excited, it's relaxing, it's going to be excited again. So fluorescence lifetime is tau fluorescence. So 1 over tau fluorescence is equal to Kf plus Kic, essentially all the constants, KQQ. Tau f is the time for full relaxation. So we'd say that we'd say the steady state approximation that S1, the rate of change at S1 is 0. Ka S0 minus S1 over tau f. Because essentially what we're doing is being able to take out all those terms right there and simplify this down. Say that S1 is equal to Ka S0 times tau f. That makes our life a lot easier. Now, if the intensity of light from fluorescence is IF, so is KF S1, then the intensity of fluorescence is also going to be Ka S0 Kf tau f. So, because we said S1 is right there, so essentially how many molecules do we have? How rapidly do they absorb? How rapidly do they fluoresce? And then what is the time for full relaxation? Now, Kf tau f is going to be Kf over Kf Kic Kisc plus Kq quench is going to be our phi f is essentially a quantum yield of fluorescence. And for every photon is absorbed, how much do we get back? How much of these other terms are going to reduce this? What is our total yield of fluorescence compared to how this, essentially, if we absorb some light, how much light do we get back? Is it 100% efficiency or 75% efficiency? How much light are we going to get back? We invert the intensity of fluorescence. It's going to give us the equation we can deal with, which then becomes Ka over S0. Kf cancels out to give you 1, and then you have Kic, KSSIC, Kf, and then this term, our quench term. A pure intensity is less useful than the relative intensity. So we're going to compare this intensity of fluorescence to the intensity of fluorescence without a quencher. So we're going to look at intensity initial, intensity fluorescence. So without a quencher, so we can set that equal to 1 over QC, KQ over KF plus times quencher. So we can plot the relative intensity of fluorescence versus quencher concentration and give us a Stern-Volmer plot, whose slope essentially looks at the rate of quenching versus the rate of fluorescence. So now the Stern-Volmer plot has its uses, but it's nice to separate the KF and KQ. So in this case, we'll use a short excitation pulse rather than a continuous excitation. The pulse is quicker than the decay, so we can say that the change in S1 dt is equal to our KF. We don't have to worry about the absorption, and then we can look at just each of the terms without the absorption. And remember, we have that tau, so the change in S is equal to negative S1 over tau F. We integrate this. We look at the concentration of S1, relation of total S1, e to the negative t over tau F. In this limit, that the rate of fluorescence is greater than the internal conversion and intersystem crossing, we can approximate the fluorescence lifetime as that, say fluorescence is usually is much faster. Tau F is KF plus Q, well, tau F is 1 over KF plus QCQ. So it means that 1 over tau F is KF plus KQQ. If we then plot 1 over tau F versus Q, we're going to plot that essentially the slope is KQ and the y-intercept is KF. So we can look at these guys independently. So if we know how much quencher we put in there and look at how these, essentially the rate of these, how long before total relaxation. Remember, what is tau F? That's the rate of total relaxation. So, okay. Now, so we essentially, all those things will help us figure out how long does it take for this to fluoresce, how this would take to fully relax, and how does quenching play a part of this. Now, photochemical processes is distinct from photophysical in that we have to consider their rate as just another branch of a relaxation decay. The absorption excitation must occur prior to the reaction. So we have the rate of the photochemical process is K, so photochemical S1, essentially the KT of photochemical for T1. So this excitation can provide sufficient energy to initiate a reaction. With all the other photophysical processes, it may take more than just one photon to ensure a reaction. So we can actually measure the quantum yield of moles reactant per moles of photon. So how much moles do we need to react? Quantum yield can be greater or less than 1 depending on the substrate. So for example, when we excite HI with light, we form a H radical and an I radical. The H radical can go on to keep reacting, but we could also terminate with 2 I radicals bumping into form I2. In this case, the quantum yield is 2, as 1 proton reacts and forms 2 moles of HI. The 1 photon essentially reacts with 2 moles. So the first one breaks HI, but the H can react with another HI. So an easy way to calculate quantum yield is use the energy absorbed and the energy per photon to calculate the number of moles of photon actually absorbed. So we'll take the moles reacted divided by the moles of photons to get our quantum. I know that's a hot mess, but that is some of the crazy mechanisms out there. Really got to start looking at some problems in order to really put a grasp on this. Depending on what is going on, you can have all variety of mechanisms that you might have to actually consider as you work through this. Hopefully, somewhat informative. I know I'm kind of droning on near the end, but we'll work through some problems at some point, so we'll be able to see what all this is all about. Kind of hard to see when it's just some dry proofs like this. Okay. Like, please subscribe. I'll see you later.